Friends, last class we looked at the role of the functionality of the base polymer in microwave continuous vulcanization. Microwave is perhaps the only technique that allows dipole-dipole collision, and thereby heat is generated internally, otherwise known as volumetric heating. In order to effectively make use of this volumetric heating, in addition to the base polymer, fillers should also be chosen appropriately. And in this case, they have used calcium oxide. They studied the role of microwave, energy radiation, and the extrusion process in continuous vulcanization. The test recipe that is given in the table 1, it contains aromatic oil, 5 parts. Interchangeably, aromatic oil, naphthenic oil are used up to 10 parts. If you want to realize the role of process aid on the vulcanized properties, then the choice comes, should it be aromatic oil or a naphthenic oil? Aromatic oil does affect cross-linking properties. That is the nature of the cross-linking mechanism, as well as after cross-linking. Naphthenic oil, its function is purely during the course of processing. All right. So you must know this difference. And secondly, aromatic oils can be staining, meaning they leave behind some coloration, discoloration. 1 and 2, some of this aromatic oil, they migrate to the surface, and that explains the discoloration of the substrate in which it is in contact. In the table given here, across various polymer from NR to epoxidized ENR. I mean epoxidized NR. NR to epoxidized NR, 50 mole %. And in between you have other synthetic rubber. Right. And the second table describes the comparison between NR and CR and their blends. CR on its own, the internal heating is quite extensive, because you look at the microwave tunnel exit, the temperature is 200 degrees Celsius, whereas NR 148. Okay, the test procedure, etc., they are given underneath. So as we said in the beginning, you have the base polymer, you also have the filler. So regarding this filler, carbon black the carbon black, right from MT medium thermal, MT medium thermal, N990, its particle size is about 250 to 300 nanometer. The finest is the ISA. Right. So the right from the coarser filler to the finest filler. The microwave energy generated or internal heat generated, you have the particle size data given. FEF is about 43 or 45 nanometer. ISAF 22 nanometer. HIF 28. So you may have studied the rubber materials, carbon black, particle size particle size is responsible for the reinforcement. Particle size combined with the structure. FEF is the most preferred filler that combines processing as well as the N properties. Processing and N properties. FEF. And this table describes a non-black filler. Table 3 describes a non-black filler with the two different irradiation. Uh, 214 zinc oxide, clay, whiting, and silica. As we see, silica, it imparts a higher energy. Zinc oxide, the least. Clay as well. Moderately whiting. So whiting is what? Calcium carbonate. Calcium carbonate. Calcium carbonate, it is also used as a partitioning agent. 1 and 2 as anti-tack. So there are additives that promote the tackiness. But handling NR, as we do the repeated mixing, NR undergoes uncontrollable reduction in the molecular weight, and that makes the compound difficult to handle. It is too sticky. So to prevent that unnecessary sticking, whiting or this calcium carbonate as a partitioning agent is coated over the compound. Is coated over the compound, and the compound is also cooled. So on contact with the water surface, so considerably the short chains on the surface, they are made inactive, and even after the cooling, certain rubber compounds are tacky. So to prevent that, this whiting is added as a partitioning agent. Whiting as a filler, so that is how we save the compound cost. Whiting, clay, we save the compound cost, control the price, make the rubber product cost effective. All right. And The table 4 describes the role of extrusion rate on the heat generation. As we see, extrusion rate is the rate at which or the screw RPM. Okay, you screw RPM, you double it or increase it further and understand what happens to the rubber compound temperature. We notice that there is increase in the temperature. Right. So microwave heating is primarily to take the compound close to the vulcanization temperature. So vulcanization is complete in the hot air tunnel, microwave tunnel, hot air tunnel. So microwave, what does it do? It prepares the compound. Heating is generated internally, and the vulcanization is complete in the hot air tunnel. All right. So, friends, this formulation. Look at the filler and the oil. The filler is 550 at 120. Aromatic oil correspondingly it is increased, so that you maintain the hardness. Whiting, of course, is not to affect the hardness anyway. Whiting job is primarily to control the tackiness. All right, control the tackiness. And what is the rubber used? EPDM. And EPDM is one polymer, and we saw in the last class that its rubberiness window can be expanded. You can add more filler, more oil, so that you maintain the hardness. Of course, tensile strength, modulus, abrasion resistance, they are definitely not as good as a hydrocarbon rubber. But for the molded rubber product, as a molded rubber product, EPDM is considered the best. For a dry air atmosphere, if the contact medium contains some solvent vapor, then we look at the nitrile rubber. So EPDM for the dry atmosphere, nitrile rubber for the atmosphere with the organic fumes. Okay. At the same time, nitrile rubber cannot support this much of filler and the oil. Right? EPDM is special. Right? So most of the rubber industries today, particularly small and medium, they capitalize on the compounding avenues in EPD. One can add filler and equal quantity of oil can be added. Friends, please note this is EPDM and the oil added is aromatic. Aromatic is considered slightly polar. EPDM is non-polar. Aromatic oil can go with the chloroprene, NR, SBR. But here, in place of paraffinic, they have used aromatic oil. Why? Right? The answer lies in the process. What is the process? Microwave radiation. Microwave radiation. And aromatic oil, they contain the unsaturates. Unsaturates, you have 5 electrons. Okay. Those 5 electrons, whatever the density that is present, is just right enough to allow the rubber chains to undergo mutual collision. This collision is necessary for the volumetric heating. All right, you cannot get that kind of volumetric heating with an arsenic and paraffinic. So aromatic oil, even though it is not the best candidate, best process oil for EPDM, the objective here is different. The objective is to enhance the volumetric heating of the rubber compound. And so, friends, table, so the previous case, table 4 and table 5 describes compression molding and hot air cure vulcanization. Definitely, compression molding, the consolidation is better. Okay? There is a molding pressure. In case of continuous vulcanization, the consolidation is not that effective. All right. So that reflects in terms of the properties after vulcanization. So look at the tensile strength difference, even though it is marginal, right? Look at the hardness, 57 for the microwave, 60 for compression, right? So compression molding 180 degree for 2.5 minutes. Friends, compression molding for NR, right? 180 degree, right? And so definitely I cannot have a polysulfidic, meaning I will have to limit the sulfur quantity. So that's why the formula is contains a sulfur at 1 part. Accelerator is 2 part. Sulfonamide CBS is a sulfonamide, and this is uh, most sought after sulfonamide until recently. CBS this base replaced by TBBS. Make a note. CBS replaced by TBBS. So what is the difference? I write here. TBBS replacing CBS. Why? And certain sulfonamide accelerators, including thiurums, and sulfonamides, even thiazole, after all, sulfonamides they decompose and liberate thiazole. All right, thiazole. Certain dithiocarbamates. Why I list all this, I will tell you. Dithiocarbamates or nitrosamine as byproduct. What they do, they generate nitrosamine as a byproduct during vulcanization. And TBBS is free from nitrosamine liberation. Okay, nitrosamine. What is the concern with the nitrosamine? Its fumes are harmful. Continuous exposure to the fumes and the atmosphere filled with the nitrosamine, it is definitely not the ambient air. And nitrosamine in certain animals was proved to be carcinogenic. And for human consumption also, right, they can be harmful, right? Therefore, our choice of rubber additives, they are called fine chemicals, complex reactivity. They are fine chemicals of a complex reactivity. Make a note, fine chemical and complex. Why they are fine? Not they have a specific functionality and we use them in limited quantity. That's why we call them fine chemicals. Specific functionality, limited quantity. Why they are complex? On their own, they have certain reaction. In combination with the other ingredients, they have other reactions, right? So they have an individual effector and an interactive influence. Individual effector, interactive, right? One well-studied interactive effector we discussed last class, synergism. Synergism between the accelerator like sulfonamides and thiurons, and the synergism between the paraphenylene diamine anti-ozonant and antioxidant like TDQ, right? The condensate of aldehyde amine. Okay, they have a positive interaction. There is an antagonistic influence, meaning if they are present are added at the same time, they have a opposite influence on the rubber. A good example is the amine type anti-ozonant and peptizer, right? And amine type anti-ozonant and the sulfur accelerator. Why? They make the compound scotchy. Peptizer and amine anti-ozonant. What is the effect? Peptizers are used as a radical scavenger. They isolate the free radical generated, free radical of the rubber macromolecule. They isolate. That is what we require in mastication or peptizing. What the anti-ozonants do, they prevent this free radical. They rather add to the stability of the rubber chain. You understand? So that is where the antagonist is. So you have a synergism as well as the antagonism. All right. So the order of addition does matter, not only in the open mill mixing, even in the internal mixing also. All right. So that is one aspect. When it comes to the health hazard, that is during the course of compound preparation as well as product making, the fumes that are liberated, they can be harmful. One. And two, some of the byproducts in the rubber product, they may get leached. They may get leached. How they do? They migrate to the surface and they get wiped off, right? As they pass through the water stream, the surface film is getting wiped off. Therefore, the waterways are getting contaminated. You follow? And there is nothing wrong with the base polymer. The problem is the choice of right additive. Choice of right additive. After all, we use rubber to support a large recoverable deformation. Large recoverable deformation. Wherever this requirement is there, we look at the rubber, right? And rubber has fulfilled this requirement perfectly. But poor understanding of the rubber composition and its limitation will create a lot of problems. This is like working with the nuclear chemistry. Nuclear chemistry, and we know the energy generated is so huge, and what we do? So we trigger the nuclear reaction. As a chain reaction, it goes on. A lot of energy is generated, and it is effectively captured, and we produce electricity. The same nuclear chemistry, if we make it as a missile or as an ammunition, it is definitely harmful to the mankind. Therefore, the who is handling what? So that is where the difference is, right? And if you look at the the working with the nuclear energy history, at least from 1945, right? 1945. So in the month of August, Japan was bombed on two different dates. So the mankind has not learnt enough lesson, right? And of course, uh, there are countries which rely only on safe fuel or energy is the nuclear energy, safe. At the same time, if it lands in the wrong hands, then we are in trouble. And it is definitely true with the rubber compound, rubber product. You have no issue in handling the fine chemical, process it, make a product out of it, but how it is used, right? And so there is always a word of caution. And rubber, as we know, it is prone to abrasion. So this abrasion, they leave behind a very fine debris meaning a very fine debris, that is the rubber particles getting separated from the product. Separated from the product. Okay. What happens? Separated from the product. Right. And get into atmosphere. Number one. And waterways. Right. So these rubber particles are harmful. Why? They are non-biodegradable. They cannot degrade that easily. Non-biodegradable. And by some means, if we consume the water or if we uh, inhale the air containing rubber particle, nothing wrong with the rubber. Again, I tell you, the It is the lack of understanding. Okay? That is similar to the plastic pollution. Plastic pollution, plastic on their own, they don't harm. They don't pollute. It is the film, okay, usable film, single-use film of thickness less than 50 micron. They litter our atmosphere, and as a result, the community reacts to the plastic saying, say no to plastic. We simply cannot say no. Right? It all depends uh, how we understand and educating the society. Okay? And rubber is another example that has even after its use, one can recycle, reclaim, recycle, reclaim. Recycle, reclaim, and like any other thermoplastic, even after the rubber product has lost its rubberiness, there is some more material remaining, right? And we use it. Okay? All that you will study in the recycling. All right. So, friends, look at this recipe in table 6. Very interesting. There are a couple of points we must take note of. One uh, is that ethylene thiourea at 2 parts. Very unusual. 2 parts is it's on the higher side. Normally, it is about zero 0.8 pHr. It is ethylene thiourea right here. Ethylene thiourea in neoprene W, ETU, right? This called in the industry, it is identified as a Na22. Right? Na22, it carries a ETU plus some carrier, similar to dicamyl peroxide, similar to dicap 40C, meaning active dicamyl peroxide is 40%. The remaining is formed by the China clay or a calcium carbonate. That is to make it easily dispersible. Okay. Same way, this Na22 0.8 parts. Here, I have used 2 parts. So what is the idea? The idea is effectively capture the sites, Q sites created by dehydrochlorination. Dehydrochlorination. Dehydrochlorination because of metal oxide, magnesium oxide, zinc oxide. This ethylene thiourea, what does it do? It just gets inserted. Similar to sulfur in dye in rubber, ethylene thiourea gets inserted. Very important. As a result, it is able to maintain the flexibility. Neoprene W, after vulcanization, maintains the flexibility. All right. And the combination of MC wax, last class we saw MC wax and 6-PPD. 6-PPD is a chemical anti-ozone. MC wax is a physical, right? So the wax plus 6-PPD is again a synergy sum, right? Synergies in terms of handling the ozone attack, right? You may ask, there is a question of ozone attack in chloroprene, sir. For sure, it is far better than NR, but still we have concern ozone attack in chloroprene rubber because chloroprene, every monomer there is an unsaturation, right? And about 2 to 3 mole percent, listen very carefully, 2 to 3 mole percent, they isomerize and we get allylic chlorine, allylic chloride, not chlorine, allylic chloride. Allylic chloride is reactive. That takes part in the cross-linking. So what is left behind? The rubber continues to have unsaturation even after cross-linking. This unsaturation is definitely prone to ozone attack. You understand? And ozone is why it is considered deadly. The concentration of all in pphm, ozone in pphm, ozone concentration in pphm, parts per 100 million, meaning for every 10 raised to, right, that is parts per 100 million, meaning the concentration can be 40 to 100 pphm. So this is the concentration at which in the laboratory it is tested. Laboratory test is mostly accelerated aging, right? So that why we accelerate the certain reaction in the laboratory, we accelerate so that we get the data points and prove that the formulation is effective. All right? So that is the idea. Ozone concentration, it is definitely higher. I'm sorry, not 400. Sorry, 100 at a different temperature. Temperature about 40 degrees. Okay. This ozone concentration, even at 40 parts out of 10 raised to 8 atmosphere. So just imagine in an atmosphere concentration of 10 raised to 8, ozone, how much is the ozone? Just 40 to 100. Right? Almost it is negligible or one can ignore. But when it comes to the ozone, you simply cannot ignore. That way, this MC wax 6-PPD combination, it works well in polychloroprene. Definitely in case of a hydrocarbon rubber like NR and SP. Okay. All right. So this is the maybe one of the rare formulations we come across on ENR. ENR, calcium oxide and zinc oxide. So this calcium oxide is necessary for ENR. That to 50. In addition to promoting the volumetric heating, it also helps in uh, cross-linking activity of ENR. Okay, all right. And this compound, it can be scorching. That's why you have a PVI, pre-vulcanization inhibitor. What is this? CTP, N-cyclohexyl thiothalamide, CTP. N-cyclohexyl thiothalamide. This is a PVI, not a retarder. It's an inhibitor. All right. And you look at SMR, PVI 0.1, SMR, CV, constant viscosity, natural rubber, 0.1 there. In case of ENR, it is 0.5. The compound is a little more curant because of the epoxide content. So this comparison again tells you the difference between microwave and the compression length. Right. So look at NVR, 27 ACN, just at the borderline, not exactly low ACN, just medium ACN, just at the beginning. 27 ACN content. This recipe is designed for a balance between low temperature flexibility and solvent resistance. What is a filler? Filler is SRF N774, right? N774 in neoprene also, but there the quantity just 5 parts, just to make the compound just a grayish, not for any filler. So filler in chloroprene is a whiting only, whereas in NBR, what is the filler? Filler is the SRF. All right. CPS, TMTD, sulfur, it should have been the order of addition, should have been just after the rubber, should have been added here, after just prior to zinc oxide. Prior to zinc oxide, sulfur should have been listed. Okay. So what does it tell you? So the press cure influence is definitely noticeable. It gives a best tensile strength 18 MPa, elongation 450. What is the hardness? 65. 65 hardness nitrile rubber from a SRF of 70 parts. 70 parts. Right. So that is about the rubber compounding for microwave medium and the choice of additive, etc. Right. With the time remaining, I take you to rubber chemistry, page number 32. What is special about the page number 32? Rubber chemistry, yeah. Rubber chemistry, page number 32. So most of this we have discussed in this particular file, but we are just revisiting page number 32. Yes. And in the last class, friends, we were looking at chloroprene rubber in two different modifications, sulfur modified, Kapton modified. So G type sulfur modified peptidable. W type mercaptan modified because it is capped with the alkyl mercaptan. SR is the mercaptan. And the G type, we have a polysulfidic link. So what does it do? Sulfur-sulfur bond energy is much less. Sulfur bond energy is rather more reactive or more labile in the sense it can undergo cleavage. As a result, one can do the peptiding. Please note, G type is a peptidable grade of chloroprene rubber. W type is non-peptidable. So W type, most of molded rubber products we make. 1 and 2, it can come with the unpredictable low temperature flexibility. In second case, low temperature stiffening is reported. Whereas G type sulfur modified, you are free from that. Right? You are free from that. Meaning this sulfur modified low temperature flexibility, you have no problem. Whereas W type, we may encounter stiffening on storage. Right? So this is the comparison between G and W type. Right? SBR, even though SBR emulsion grade is marketed at a viscosity of 50 Mooney viscosity, there are occasions where we'll have to reduce the viscosity. So there one has to use a higher dosage of peptidizing. So SBR can also respond to peptidizing. Only thing, we use a higher dosage of the Renacid 7 or similar peptides, right? I'm sure you have gone through, because maybe if you want to understand the peptides chemistry, we will do it later. But I expect you to do some self-study or just revise whatever you have studied in the rubber chemistry, because NR in the absence of a peptidizer, right, that understanding is incomplete. So I strongly suggest you revisit. If you have doubts, feel free, we can discuss. All right. So friends, in the next class, we will take up certain hardness specific formulations. All right. That you will find it very interesting. Right. So friends, with this, I don't want to hold you further because we have another class in the 4th period. I stop here. Right. Thank you. Take care.
Yes, sir.